Welcome to Chapter 23, Electric Current. We are going to talk about the flow of charge, electric current, voltage sources, resistance, Ohm's law, direct current and alternating current, the speed and source of electrons in a circuit, electric power, CFLs, LEDs, and electric circuits. Okay, now when you have the ends of an electrical conductor at different electrical potentials, there's a potential difference between them, and charge will flow from one end to another. It's very much like water flowing from higher pressure to lower pressure in a piping system. Now, to attain a sustained flow of charge in a conductor, you have to make an arrangement to maintain this difference in potential to keep the charge flowing. Otherwise, what will happen is it'll stop. As soon as these two, for instance, like here's a water system. Once these two become the same height here, the same pressure, the water doesn't flow anymore. So what they do is they put a pump in here. The pump continuously pumps the water up to a higher pressure and allows it to flow through the system. This is very much like this. The water is the flow of charge, the electrons in the circuit, and the pump is the battery, and this, of course, is the resistance to this, otherwise known as a device or the load. Now, electric current is the flow of charged particles. In metal wires, it is due to electrons, and these are the conduction electrons. These are the charge carriers. They're free to move throughout the atomic lattice. Protons themselves are bound with the nuclei of the atom. They don't move. In fluids, you can have positive ions and electrons to constitute electric charge flow. In a plasma, it's basically positive ions and electrons. Now, which of these statements is true? The electric current is a flow of electric charge. Voltage is stored. It's not current. The voltage will produce a current in a connecting circuit because it's basically the electrical potential. The battery will move electrons already in the wire, but not necessarily those in the battery. The rate of electric flow is measured in amperes. Amperes is, by definition, is a coulomb of charge flowing past a point per second. The speed of electrons, which is the drift speed through the wire, is actually extremely slow because these electrons are trying to get through, all bumping through the wires, and this bumping back and forth is actually the resistance, and it heats up the wire. But the signal that tells the electrons to start moving travels at very nearly the speed of light in vacuum. So this means you can have a very long wire, and yet you turn on the light, and you can see the light, the signal goes all the way down to the end of the wire almost immediately. Charge flows through the circuit. The voltage is established across the circuit. Now, alternating current. We were talking about DC before. Alternating current, the electrons oscillate to and fro around fixed position. The movement is produced by the generator or alternator that switches the sign of the charge repeatedly. Commercial AC circuits are used in most residential circuits throughout the world and can be stepped up to high voltage for transmission over great distances. And it's very efficient to transmit electricity at high voltages, as you keep the current as low as possible, and that keeps the loss. The loss is related to I squared R, the current squared times the resistance. So we try to keep the voltage as high as possible, which keeps the current as low as possible. A conductor is any material which has free charge particles that can easily flow through it when electric force acts on them. Examples of good conductors are any metal, acids, bases, salts dissolved in water, molten salts, plasma. Anything of the potential difference in voltage is high enough to overcome the resistance of the conductor. This is called breaking down. So you have to be very careful. Any insulator can become a conductor under the wrong conditions. The electric potential difference is basically the difference in potential between 2 points, and charges in a conductor will flow from higher potential to low potential. It's sort of like the pressure difference between two ends of a pipe. If you have a pressure difference between two ends of the pipe, the water will flow down the pipe. If you have a potential difference between 2 points in a circuit, the charges in the conductor will flow from the higher potential to lower potential. The flow of charge will persist until both ends of the conductor reach the same potential. And if you want to keep it flowing, you have to put some sort of device in there to maintain that potential, something like a battery, a fuel cell, a photovoltaic cell, or a generator. And voltage, of course, is measured in volts. Now, if you have water from a higher reservoir, it'll flow to a lower one. And it'll keep on doing that until these two are the same height. In other words, until the pressure difference between them disappears. And when that happens, then the flow of charge ceases, just like the flow of water ceases. So in order to keep the water flowing, or in order to keep the charge flowing, you have to have a battery or a generator to maintain the steady flow of charge. It's like putting a pump in this circuit here. And this is pretty much analogous to that. And what is going on is here, the work is done in pulling negative charges apart from positive ones, and electromagnetic induction at the generator terminals provides the electrical pressure to move the electrons through the circuit. For a battery, it's basically converting chemical energy to electrical energy. That's what batteries do. Generators usually convert mechanical energy to electrical energy. Now, in chemical batteries, the batteries, well, they work by chemical disintegration of the material inside the battery, and the energy stored in these chemical bonds is then converted to electrical potential energy. Now, the current in a circuit depends on the voltage and the electrical resistance in ohms. And you can put resistors in the circuit. Resistors are circuit elements that regulate the current inside of electrical devices by changing the overall resistance of the circuit. And here's some pictures of resistors. Here, of course, this is a potentiometer. This actually is a variable resistance. These other ones are more or less constant. A symbol of resistance in an electric circuit is a zigzag line. And if you ever take apart a device, please don't do that unless you know what you're doing. Because you can hurt yourself. There are some things in there that can hurt you even if it's not plugged in. So don't do it. If you might ever see something like this, maybe an old piece of electronics gear, and if you look inside there, you see a bunch of these cylindrical things, these little cylindrical things, and they have all these bright colors painted on them. Those are resistors. Usually they're resistors, and they have a color code. The bright bands that they paint on them are basically tell the value of the resistor, how much resistance there is. The first band is the first digit. The second digit is the second band. The third digit is the multiplier. The last band is the tolerance. So this one, if you look here, here's the color code. The first digit, that's red, that's a 2. The second digit is green, so that's a 25. The third digit is a multiplier, that means there are 3 zeros after that 25. So this is a 25 kilo ohm resistor and has a tolerance of plus or minus 10%. Now, there are several factors affecting electrical resistance. It's inversely proportional to the cross-sectional area of a wire. So if in a given wire, more thick wires will have less resistance than thin ones do. It is directly proportional to length. If you double the length, you double the resistance. It's just like having a longer pipe. Long, thin pipes don't carry much water. They have a high resistance to the flow of water. In wires, electrical things, material has an important thing to say too. Rubber is much more resistant than carbon, which has much higher resistance than copper of all the same size. Each material has its own characteristic resistivity, and on top of that, the resistivity of the material usually depends upon the temperature. Resistance is length times resistivity divided by area, and we write this as R equals rho L over A. Rho is the resistivity. A is the area, and L is the length. Now, as I mentioned before, resistivity changes with temperature. Usually, the higher the temperature, the higher the resistance, and that's for metals. Semiconductors can show the opposite effect. And what goes on in metals, especially the thermal jiggling of the atoms in the metal impedes the electron flow. Now, in semiconductors, refer to materials that can alternate between being conductors or insulators. Resistivity can be adjusted by adding small amounts of other materials such as doping. Resistivity can decrease with temperature in semiconductors. Examples of semiconductors are germanium, silicon, and carbon. Now, superconductors, don't get these confused with semi. They look alike. So when you're taking a test, I almost misspoke there. So I'm going to leave that when I try to edit this. I'm going to leave that in there. Superconductors have zero electrical resistance to the flow of charge. And this means that there is no heat generated when charge flows. This only occurs at very low temperatures, close to 0 Kelvin. And the search is on for room temperature superconductors. The problem with these, there are some kind of high temperature superconductors. That means they're not exactly at absolute zero. These refer to ceramic materials that can carry much current at a very low voltage, but they're still so well below room temperature they require special cooling, usually liquid nitrogen. And on top of that, they're very expensive alloys, hard to find alloys, and they're brittle and hard to work with. Now, Ohm's law states is the relationship between voltage, current, and resistance. It states that the current in a circuit varies in direct proportion to potential difference or voltage and inversely with the resistance. So I equals V over R. Now, for memory, for the ease of memory, I remember VIR. V equals IR. VIR, just remember that word, VIR. And of course, you can always turn it around and write I equals V over R. So for an example, if you have constant resistance, if you want twice as much current through a device, put twice as much voltage across it. Unless you know what you're doing, please don't mess with electricity. If you have twice the resistance and twice the voltage, the current will be unchanged. Now, resistors are circuit elements that regulate the current inside of electrical devices by providing specific resistances. When you double the voltage in a simple electrical circuit, you will double the current, okay, because the voltage is on top of the Ohm's law. Now, electrical shock is usually not something you want to encounter because shocks can actually damage your body because current passes through your body. And they're caused by electrical potential difference between one part of your body and another. And that will depend how much shock you get. What happens depends upon body conditions and specifically, typically to resistance. Usually it's how dry your skin is. They always tell you that electricity and water don't mix. Well, in reality, they mix too well. If your skin is wet, the resistance to the flow of current might be as low as 100 ohms. If your skin is really dry, it might be 500,000 ohms. And you can kind of imagine this is much worse than that when you're much more likely to get a large current through your body. Anything can become a conductor if potential difference across it is high enough. So be very careful. Now, a bird, people ask me this all the time, and I can remember asking my dad this when I was a little kid. If you look at the top of wires up on top of telephone poles, most people think they're insulated. They're not. Those are usually bare. And birds perch on them with their little bare feet. And suppose a bird is perching on a high tension line carrying 2,500 amps, current of 360 kilovolts. If the line has a resistance of 2.5 times 10 to minus ohms per meter, and the bird's feet are 4 centimeters apart, what voltage does the bird feel? Well, the resistance of the wire between the bird's feet is 2.5 times 10 to minus fifth ohm per meter times 0.04 meters. And I don't know why this thing keeps doing that all the time, but that's PowerPoint. This is 2.5 times 10 to the minus fifth. That's an exponent. PowerPoint loves to get rid of exponents. And once it does it once, you can never get it to stop. The voltage difference across this resistance, it will be V equals IR. So it's 2,500 amps times 2.5 times 10 to the minus fifth ohms per meter times 0.04 meters. And this is, of course, the units conversion. It's 2.5 millivolts. The bird will never feel this, even if he's soaking wet with salt water. Now, as long as the bird stays on his wire and touches nothing but the wire, he's perfectly safe. If he touches ground while holding on the wire, he'll be a fried bird. Now, there's two basic types of current, direct current and alternating current. Direct current, as its name suggests, flows in only one direction only. So this means the electrons are always moving from the negative terminal toward the positive terminal. Alternating current is given the shorthand format AC. In this case, of course, you notice that the polarity of this reverses all the time. It goes from negative to positive continuously, back and forth. And this what happens then is the electrons in the circuit are sloshed first in one direction and then the opposite direction. So they alternate to and fro about fixed position. They sort of dance back and forth in place. This is accompanied by alternating the polarity, the voltage of the generator or other voltage source. And how this works is basically, this is an electromagnetic sine wave. We'll talk more about that later. But electromagnetic waves do one thing, they carry energy. Commercial electricity in North America is AC. Is 60 cycles per second, and at your house, inside your house, 120 volts. Now, it isn't very efficient to transmit energy over long distances, high voltage. So Europe adopted 220 volts as its standard, but the US already had the 120 volts in place it was too much trouble to change it. But it's easy to change voltages, just put transformers in there. If you need to convert from AC to DC, and this is of course done, say in your power supply for your computer. Household current is AC, but currents in laptops, TVs, LED lights is all DC. And what they do is they put a diode in there. A diode is a tiny electronic device that acts as a one-way valve. It allows electron flow in one direction only. And what you wind up with is something that looks like this. Here's the incoming AC. Here's what happens when it goes through a diode. It only allows the top to occur. What they usually do is they rewire this so that you end up getting this too. So it fills these in. So you wind up with something like this. So there's no gap in current output. A pair of diodes will reverse the polarity of the alternate half cycles instead of getting rid of them. Then they put capacitors in here. Capacitors will store charge and then release it. And this is used to smooth out the ripples. It's called filtering. The better you filter this, the more like a DC it becomes. When we flip on the light switch on the wall and in the circuit, an electric field, which is called the signal, is established inside the conductor. The electrons are moving around in there. Even when there isn't a signal on there, they're moving because just the thermal motions, these random thermal motions, keep them moving. But when you put on the signal, when you put an electric field across the two ends of the conductor, that causes the electrons to they continuously move, but instead of just going randomly, now they're kind of floating along. in a direction. And this current is established through the wires. The actual establishment of the current occurs at nearly the speed of light because the signal travels very quickly. The electrons themselves move extremely slowly. Speed of light is 3 times 10 to the 8th meters per second. The electron drift is 0.0001 meters per second typically. But it's the electric field that travels nearly through the wire at nearly the speed of light. So the light, it gets there. When you turn on the light switch, you don't have to wait forever for the electricity to get to the end of the wire. Now, if the voltage source is DC like a battery, there are electric field lines that are maintained in one direction in the conductor. And of course, then the conduction electrons in the wire are accelerated by the field in a direction parallel to the field lines. And of course, they're in a wire. They are in with other electrons, other metallic ions in their paths by bumping around, transfer some of their kinetic energy to them. And this kinetic energy, of course, just remember thermodynamics, it has a tendency to appear as heat in the wire. And this is due to the resistance of the wire. And we call that I squared R loss. Why? Because it's equal to the square of the current times the resistance. Now, there's some misconceptions about electric current. One of the misconceptions is current is propagated through the conducting wire by electrons bumping into one another. That's not true. Electrons are free to move in a conductor. They're accelerated by the electric field that's impressed upon them. True, they do bump into one another and other atoms, but this slows them down and offers resistance to their motion and heats the wire. Electrons throughout the entire closed path of a circuit will all react nearly simultaneously to the electric field, which itself travels at nearly the speed of light. Electrical outlets in the walls of homes are a source of electrons. This is not true. The outlets in homes are AC. The electrons don't make any migration through the wire in an AC circuit. They just dance back and forth in place. So when you plug a lamp into an outlet, the energy flows from the outlet into the lamp, not the electrons. Energy is carried by the pulsating electric field as an electromagnetic wave inside the wire. This causes vibratory motion, and this is the electromagnetic wave, just like light. It's just an extremely low frequency, long wavelength wave. We'll talk more about that later. Electric utility companies sell you energy. If you look at your energy bill, it's a kilowatt hour. Power times time is energy. You provide the electrons in the wire. Electric power is the rate at which electric energy is converted to another form. In equation form, it is current times voltage. The unit of this is watts. And of course, energy is also power times time. So for example, you have an old-fashioned 100-watt light bulb. It draws 0.8 amps to 120 volts. Run this bulb for 1 hour, you'll burn 0.1 kilowatt hours of energy. And in typical places around in Michigan, that costs 1.6 cents. A modern LED equivalent will only use 15 watts in 1 hour. It will only cost you 0.24 cents. And it will only burn 0.015 kilowatt hour, which is why, if you can, convert to LEDs. The problem with incandescent bulbs is they dissipate 95% of their energy in the form of heat. And they're great for snakes. Snakes can see in infrared light, especially pit vipers like rattlesnakes. That's how they hunt their prey. Well, we're not snakes. We don't see infrared light. We see visible light. So they're not energy efficient. So instead, a fairly long time ago, fluorescent lights were developed. These emit much less heat, which is why you can touch them without burning yourself. CFLs are more modern. They're a type of fluorescent lamp that fits into a standard light bulb socket. But at the same wattage, CFLs emit much more visible light and much less heat, which is infrared light, than incandescent bulbs. The downside to these is that they contain mercury, which is toxic, and they break very easily, which will release the mercury, which is dangerous. Now, a much better option is LEDs. These are the most modern form of lighting. And these are basically, these have been around, if you look at your little computer lights that tell you when your hard drive is running or tell you when your stereo is on or off, they've been around for dozens of years. The modern ones are much more powerful, and they're much more efficient as light sources than CFLs. And they last longer. They're up to 20 years in normal use. They're safer. There's no mercury. They're rugged. They don't break even when you drop them onto a concrete floor. Between CFLs and LEDs and common use incandescent bulbs, you would be much better off. If you have a choice, get LEDs. You'll be much better off. A circuit is any path along which the electrons can flow from the negative terminal to the positive terminal. And a complete circuit is necessary to allow the continuous flows of electrons. A complete circuit means there's no openings or gaps. Now, any break, which is usually caused by opening a switch or disconnecting something, will stop the flow of current. Circuits have two common ways of being connected. One is a series circuit. A series circuit means that there's only one path for the electron to flow between the terminals of the battery, generator, wall outlet, and all of the current is in that same path. A parallel circuit, there are branches, each of which is a separate path for the flow of current or the flow of electrons. Now, series circuits look like what I call a daisy chain. You can see that there's only one path. So there is, as I say, the total resistance of current is the sum of the individual resistances. The current is equal to the voltage supplied by the source divided by the total resistance of the circuit. Now, series circuits, the total voltage you press upon a series circuit divides among the individual electrical devices in the circuit, so the sum of the voltage dropped across the resistance of each individual device is equal to the total voltage supplied. And we can write that as the sum of voltage drops equals the sum of voltage rises. This is as a consequence of the law of conservation of energy, because voltage is related to energy. So in other words, if this has one voltage drop, 1 volt across it, this has 1 volt across it, that has 1 volt across it, that means the total is 3 volts, and that's a 3-volt battery. If you want these to light, you've got to have a 3-volt battery. Okay, the voltage drop across each device is proportional to the resistance. V equals IR, what I call VIR, is the same throughout the circuit. So in other words, you look here, there's no place else for it to go. So this current here is the same as that current there is the same as that current. If something breaks the circuit, if one of these bulbs burns out, the whole thing stops. It's the old-fashioned Christmas tree lights. Remember them? Yeah, they're not much in use anymore because they're frankly a pain in the butt. But they also use series circuits in parts of circuits with fuses or circuit breakers, because the fuse or circuit breaker sees all the current in that part of the circuit and can shut off all the current at one time for safety. Now, parallel circuits are a lot more common. Parallel circuit provides multiple paths for the current to flow. And so, for instance, here's the total current. And if you sum up the current in this branch plus the branch plus that branch, you end up with the total current. The voltage drop is the same across each device. The total current is the current in the circuit divides among the parallel branches. The amount of current in each branch is inversely proportional to the resistance of the branch. If you've ever heard the expression, electricity takes the path of least resistance, so the most current will end up in the path of least resistance. The total current in the circuit will equal the sum of the currents in the parallel branches. So this has 1 amp, this has 2 amps, and that has 3 amps. Okay, obviously that's not when the switch is open, it's when it's closed. 1 plus 2 plus 3 gives you 6 amps in here. Now, a parallel circuit, as the number of parallel branches is increased, the overall resistance of the circuit decreases. You have more paths for the current to flow, and more paths equals less resistance. It's sort of like having extra lanes on the freeway. Current drawn from the source will equal the sum of the currents in all of the branches put together. If you break one of the paths, for instance, if you open the switch here, the current only in that path stops, the rest of them stays lit. So a break in one path does not interrupt the flow of charge in the other path. And this is used everywhere. Most household circuits are parallel. Now, when two identical lamps in a circuit are connected in parallel, the total resistance will be less than the resistance of either lamp. It's like extra lanes on a checkout counter or extra lanes on a freeway. More lines means less resistance, allowing for more flow. Consider a lamp powered by a battery. Charge will flow through both the battery and the lamp. Charge is already in all parts of the conducting circuit. The battery just gives the oomph for the charges to move. It makes them move, is what it does. As much charge flows in the batteries outside, so therefore charge is flowing throughout the entire circuit. And you can tell that if you break the circuit, charge stops. There's a problem with parallel circuits in a house. Because these are all in parallel with each other, as more and more devices are connected into the circuit, more and more current is flowing through this part of the wiring here. And there's an amount of current that each wire or device can carry before it overheats. When the current is excessive, overheating can result in a fire. So they put circuit breakers installed in series with the entire circuit breaker or fuse. Of course, this fuse will see all of the current, the sum of all these currents, and that allows the fuse to cut off the entire circuit at the same time, also sense when this is starting to overheat. Now, breakers are also installed in individual devices to break the current flow if it gets too excessive in a device. So, for instance, especially in heaters and toasters, because these things typically draw a lot of current. So you want to make sure you keep that safe. If you add too many devices in a parallel circuit, you increase the amount of current moving through the wires. This can produce an overload and overheating the system. And unless you've got the circuit breaker opens or the fuse blows, you can end up with a fire in the walls. You do not want fire in the walls. So we put circuit breakers or fuses in that to interrupt the flow when the current gets too high. Now, safety fuses have thin wires that melt when a given current is exceeded, and they're connected in series along the supply line to prevent overloading in the parts of the circuit that need protecting. And now we are replacing those by circuit breakers in modern buildings because it's a pain in the butt. If this burns out, you got to take off, get another fuse and replace it. Circuit breaker, they have a little switch that you can push in and the breaker will reconnect. Circuit breakers are automatic switches that turn off when the current is excessive. Now, the fuse or breaker both work pretty much the same way. They interrupt the circuit, just like opening a switch. That shuts off the flow of current if it senses too much current that's flowing through it. Usually, the fuse or breaker uses the heat generated by the current flowing through it, a sensitive element to detect excessive current. And the circuit breaker can be reset after the overload has been corrected, but the fuse has to be replaced. It is always important to correct the problem which caused the overload. The problem could be too many devices plugged in and drawing too much current, that's an overload, or a wiring fault, such as a short circuit, otherwise known as a short. Never replace a fuse with a fuse of a large rating. The circuit, is protecting the fuse, which is not what you want. Then you'll wind up with a wall fire. Okay, electrical safety. One of the best, most important things is to stay dry. Dry skin has a much higher resistivity than wet, so be careful when you're working around water. Stay off the wet ground when using electricity. Wet ground can complete a circuit and allow you to get a shock. Inspect cords regularly. Never use any which are frayed or damaged. Never pull the plug by pulling the wire. Grasp the plug, not the wire. Don't place cords where they can be damaged or tripped on. Keep kids and pets away. Never alter a plug. Do not break off the round grounding prong or file down the wide prong. If an appliance gives you a shock or sparks or smells like burning insulation, stop using it. It's not worth having a fire. Do not try to convert a polarized plug to a non-polarized one by cutting or filing down the longer prong. Doing so might energize the appliance and shock you. Install GFCI outlets in wet areas of your house, such as bathrooms or kitchens and laundry rooms. There's a code, I think it's 6 feet. 6 feet within a source of water. Any outlet within 6 feet of a source of water should have a GFCI in it. GFCI stands for ground fault circuit interrupter. They detect and cut off small leakage currents before they can injure or kill. And there are actually GFCI extension cords, which can be used outdoors. Never ever replace a blown fuse with one of a larger rating. Unless you know what you're doing, have a qualified electrician do any rewiring in your house, not Bubba down the street. If you blow fuses or pop breakers frequently, or there's a smell of burning insulation in your house, stop using the affected outlets and circuit. Have it checked out by a qualified electrician before you use it again. Make sure it's safe. Be sure to be careful when using extension cords and power strips. Never exceed the cords or power strips ratings. Don't use extension cords or strips that are rated for indoors use outdoors. Never place cords where they can be damaged or tripped on. An electric meter measures the amount of energy used in kilowatt hours. Never fool around with an electric meter. Do so is illegal and extremely dangerous. Keep the meter free of ice and snow in winter and wasps and birds' nests in summer. If you do get a wasp nest or a bird's nest, especially a wasp nest, be very careful when you use wasp killer spray. You want to get one that does not conduct electricity. Read the label carefully or ask the guy behind the counter at the hardware store. Never touch a down power line or anything that might be touching the wire. Treat all power lines as live and lethal. Stay at least 25 feet away. The ground can carry currents for amazing distances. If you're in a car, do not try to leave the car. You're completely safe inside the car. And yes, you can safely touch the metal inside the car. When filling up at the pump, stay outside the car. Place any gas can on the ground before you fill it up. Charge can build up on the car, the gas can, and even on your clothing. You want to keep everything at ground potential like the gas pump, or you might get a spark and a fire or explosion. During thunderstorms, stay away from plumbing, stay off the phone except wireless ones. Do not use or touch electrical appliances. Lightning can travel more than 20 miles. That's the origin of the out of the blue statement. And it can do very strange things. Never take refuge from a thunderstorm by standing under a tree. And if you're on the golf course or on the water, get into a building or your car fast. The safest place is inside a metal box, like a hardtop car or metal building. If your hair starts to stand on end, place your feet together with your ankles touching each other. Squat down. Do not lay down on the ground. Place your hands over your head. Stay as low as possible ground as possible while minimize the area in contact with the ground. During a thunderstorm, the safest place is inside a metal box, like a hardtop car or metal building. And no, it's not because of the rubber tires. If you look carefully here, there is an arc on the front tire in the picture. Modern tires have steel belts in them, and they have carbon in them, which makes the tires conduct. That's a safety issue. It allows the charge that builds up on the body of a car to drain off so that when you put fuel in the car and you put the nozzle inside the gas tank, you don't set off a spark and an explosion. So actually rubber tires are actually made to conduct. Like charges repel, and they try to get as far away from each other as possible. So the charges hang out on the outside of the conductor. They flow around the outside. So no charges on the inside. Man inside the car is safe. Another way to look at this is that the body of a conductor is an equal potential surface. So everything inside this conductor is at the same potential. Since this potential difference that kills and equal potential by surface has no potential difference, the man inside the car is safe. He can sit on this, he's sitting on a seat that has metal springs in it. He's touching the inside of the car. He's got his hands on the steering wheel. That's okay. He just can't get out of the car. If he gets out of the car, then that's a problem. So if this ever happens to you, don't get out of the car. Batteries also have their own set of rules for safety. Never try to recharge a battery that's not specifically designed to be recharged. Never recharge a chargeable battery except in the charger it's designed for. Doing either of these can result in fire, chemical burns, and explosions. Never mix new and old batteries. The new ones will die trying to charge up the old ones. You're not saving anything. Never mix batteries of different types. The higher voltage ones will die trying to charge those of lower voltage. Never dispose of batteries in a fire. Never short out a battery. If you put a battery in your pocket or purse, be careful. Metal objects like keys or even pencil lead can short it out and cause a fire and or burns. In other words, it's kind of embarrassing if your pocket catches fire. And it's a little disconcerting too. Be extremely careful when jump starting a car with a dead battery. Doing this incorrectly can seriously injure or kill you. Car batteries give off explosive hydrogen gas when they're charging, and the sulfuric acid inside of them is extremely corrosive and poisonous. The flow charge in an electric circuit is much like the flow of water in a system of pipes. Electric charge will flow in an electric circuit when there's a potential difference existing across the parts of the circuit. Electric current in a copper wire is normally composed of electrons. Now, you can have other things. Any charge, any moving charge is an electric current. But in any metal wire, the electrons are what's doing the conducting. And those are called conduction electrons for that very reason. Which statement is correct? Charge flows in a circuit. Voltage actually causes the flow of electrons and doesn't flow. Charges flow. The battery is a source of energy, a potential difference that causes the electrons to flow, causes the current to flow. If you apply heat to a copper wire, the resistance of the wire will increase. The amount of current in a circuit will depend upon both the voltage across the circuit and the resistance of the circuit. When you double the voltage in a simple circuit, you will double the current, and that's according to Ohm's law, I equals V over R. When 110 volts are impressed across a 22 ohm resistor, the current in the resistor is, well, you use Ohm's law, I equals V over R. 110 volts divided by 22 ohms is 5 amps. To receive an electric shock, there must be a difference in potential across part or all of your body. The difference between AC and DC in electrical circuits is that in DC, the electrons flow in one direction only. In AC, they flip back and forth. They move, slosh back and forth. They dance. Which device is used to convert AC to fairly steady DC? Actually, they use a diode and a capacitor. The diode will convert AC to DC. If you put a capacitor in there, you get steadiness. What travels at about the speed of light in an electric circuit? It is the electric field. That is the signal. It gets all the electrons moving at the same time. It races down the wire at nearly the speed of light and makes all the electrons dance to its tune. When you buy a water pipe in a hardware store, the water isn't included. When you buy a copper pipe, you already have the electrons. They come with the wire, so copper pipe is a bargain. The drift speed of electrons that make up the current in a circuit is extremely slow. It's worse than a crippled caterpillar, but the signal travels at almost the speed of light. If you double both the current and voltage in a circuit, the power will quadruple. Power is current times voltage. If you double both, 2 times 2 is 4. A lamp with a current of 10 amps connected to 120 volts consumes a power is current times voltage. So 10 amps times 120 volts is 1200 watts or 1.2 kilowatts. Which of these lamps is longer lasting in a common circuit? Go for the LED. We'll talk more about LEDs in chapter 30. They're really cool. In a simple circuit consisting of just a single lamp and a single battery, like this one, when the current in the lamp is 2 amps, the current in the battery is also going to be 2 amps. There's no place else for the current to go. In a circuit with 2 lamps in parallel, if the current of one of the lamps is 2 amperes, the current in the battery, now we're going to assume that the lamps are identical. If that's true, and even if they aren't, you have more paths for the current to flow. You're going to have the currents will add in parallel. So it's going to be more than 2 amps. If these two branches were exactly the same, then the current in the battery will be twice the current in one. Otherwise, it'll just be the sum. But it's still greater than it was before. And the current in the battery will be the sum of all the currents in all the branches. One way to prevent overloading in your home circuit is to operate fewer devices at the same time. So if your breakers pop, usually it's because you plug too many things in or too many things that draw too much current. Toasters and heaters have a tendency to draw a lot of current, and they will pop breakers frequently. So that happens to you. It's usually something like a toaster or heater. If it isn't that, then it might be something wrong. You could have a short circuit in one of these, in which case, unplug things. Hey, don't plug them back in until somebody checks them out. Thank you very much.